Hello, this is Jude Socrates. Today's video is about an introduction to systems of linear equations and the reduced row echelon form, also known as the rref. Now, in a class like college algebra, you've almost certainly solved systems of linear equations in 2 or 3 variables. So let's jump right in and see an example of such a system that you may have encountered. So here we have a system with 3 equations in 3 variables, x, y, and z. And in college algebra, what were you allowed to do with such a system? So there were 3 things that you could do, and we'll call them swap, scale, and sum. So for swap, you simply exchange 2 equations. For scale, you multiply or divide both sides of an equation by a non-zero number. So for example, if the first equation here had a 2 instead of a 5, then it would probably be a good idea to divide both sides of that equation by 2. You get smaller numbers, and as a bonus, x will have a coefficient of 1, and that's always a good thing. So let's bring it back to our 5. And finally, you're allowed to add or subtract a multiple of one equation to another. And by that, of course, we mean that you multiply temporarily both sides of an equation by a constant, and then you add the corresponding 2 sides of the equations to each other. So of course, we will say that more succinctly as add or subtract a multiple of one equation to another. So for example, you have a minus 2x in the second equation and a 4x in the third equation. So if you want to eliminate the x, you can just multiply the second equation by 2, both sides, and then add the corresponding sides to the third equation. Now, before we actually solve this system, let's talk about why are we allowed to do these 3 operations. And that's because if you perform any one of these operations, you do not change the solutions x, y, and z to the system. Why is that? Well, for a swap, you just rearrange the equations. So they're essentially the same equations, just in a different order. So any solution before is still a solution to the new system. Now, how about for a scale? So what if we multiplied both sides of the second equation by 3? Then it becomes minus 6x plus 9y minus 3z equals negative 3. So if x, y, and z satisfy the first equation, then they also satisfy the second equation. That's the substitution principle. Multiply both sides of this equation by 3. If this equation is true, then this new equation is also true. Now, let's go backwards. What if you knew that minus 6x plus 9y minus 3z equals negative 3 is a true equation? So this time you can divide both sides of that equation by 3, and you get the original equation. And again, that's the substitution principle. If this equation is true, then this equation is also true. So another way of saying that is that these 2 equations are equivalent to each other. They are either both true or they are both false. So now how about a sum? Let's add twice the second equation to the third equation. So we'll get minus 4x plus 4x, no x. 6y minus 7y gives you negative y. And negative 2z plus 5z gives you plus 3z. On the right side, we have negative 2 plus 1 will give you negative 1. So this is our new third equation. The second equation does not change. Now let's go backwards. What if you had these 2 equations, which we copy over here, and we want to get back the original third equation? What do? So the opposite of add is to subtract. So we subtract twice the second equation from the third equation. Or another way to say that, if we will add negative 2 times the second equation to the third equation. So we will get positive 4x on the right side. Negative 6y minus y gives you negative 7y. Positive 2z plus 3z gives you 5z. On the right side, you will get positive 2 minus 1. That gets you positive 1. Okay, so once again, these two new equations are equivalent to the original two equations. So this smaller system of two equations is equivalent to this system of two equations. You can get back one from the other. This is going to be very important to us in the near future when we're going to invert a matrix. So we will say that these three operations are reversible operations. You can recover the original system from our transformed system if you knew what process was done. One more thing that we're going to do is we are going to create what is called an augmented matrix from our system of equations. It's very tedious writing out x, y, and z all the time. So instead, as long as you keep the coefficients for x, y, and z correctly aligned when we perform our computations, you don't have to write x, y, and z over and over again. So our coefficients are 5, minus 4, minus 8, and 6. We will put that at the top row of this augmented matrix. So notice that the equal sign has been changed to a vertical bar. Similarly, for the second equation, you have minus 2 plus 3 minus 1 minus 1. Minus 2 plus 3 minus 1 minus 1. And finally, you have 4 minus 7, 5, and 1 for our third equation. So now we can think about our three operations on equations as operations on the rows of our augmented matrix. We can swap two rows, equivalent to swapping two equations. We can multiply or divide a row by a non-zero number, and we can add or subtract a multiple of one row to another row. Since our three kinds of operations on equations do not change the solutions to our system of equations, we can equivalently say that our row operations do not change the solution set of an augmented matrix. This means that if you have an augmented matrix A and you obtain a new matrix B from A using a single elementary row operation, then the solution set that you get to the new system is exactly the same as the solution set to the old system. So any finite sequence of row operations will not change the solution set of an augmented matrix. Our strategy will be to use these three kinds of row operations to get one equation containing x with coefficient 1, and then we will use this equation to eliminate x from our two other equations. This way, we will get two equations in only the variables y and z. We will repeat the strategy so that we will eliminate y from the third equation, and thus we will have only one equation in z, and then we can solve for z. Now, to actually perform the computations, we will get a little bit of help from the internet. Let's go over there. Okay, so on Google, search for linear algebra calculator. And the first hit that you get here is what we want. All right, so there are lots of good stuff that you can do on this web page, and this is the routine that we are going to use. So the first thing you have to do is input the number of rows, the number of equations that we have, and we have 3 equations, and the number of columns. Now, we have the 3 variables x, y, and z. The equals was turned into a vertical bar, and then you have the constants on the right side. We're not going to input the vertical bars. Those are going to give us an error. So it will just be 3 equations in 4 in 3 variables, and that will give us a total of 4 columns. All right, so there is our blank matrix. So I've gone ahead and typed in our matrix, and let's click on Submit. Okay, so this routine will allow us to perform elementary row operations on our matrix, and the computer will do all the work for us. So we said, okay, let's get rid of this 4 by adding twice second row to the third row. So add 2 times the second row to the third row. So there it is. We got a 0 now in that entry. Now, we do want our x to be all alone with a coefficient of 1. So the easiest way to do that is to think of 5 minus 4. Okay, so we add twice of the second row to the first row, so that we'll get 5 minus 4 equal to 1. Instead of dividing by 5, which will give us fractions right away. Now granted, the computer is doing all the work for us, but why should we look at ugly fractions, right? So let's add 2 times the second row to the first row. Okay, so we have now that 1. All right, so we have gotten rid of the x in the third equation. Let's get rid of the x in the second equation by adding twice the first row to the second row. 2 times the first row to the second row. There we go. Okay, and check it out. As a bonus, we have a minus 1 as our coefficient for y. So a good thing to do would be to exchange these 2 equations. Exchange the second row and the third row. Okay, so we now have a coefficient of -1 for y, which is almost as good as +1. Let's get rid of the 7 here for y by adding 7 times the second row to the third row. Add 7 times the second row to the third row. There you go. Ooh, look at that. So you see the last step over here, and aside from canceling out the 7, we canceled out the rest of the row. And why is that? Well, 7 times 3 is +21, cancels with a -21. 7 times -1, -7 plus 7 gives you 0. So the third row is all 0. Okay, so that might disturb you. Just hold on to that for a minute. So now, that's great. We have a coefficient of 1 for x, almost 1 for y. So let us multiply the second row by -1. And now we have +1y in the second equation. Okay, anything else we can do? Well, we don't have a z. You might say, well, what if we divide by -3 to make that a 1? But then that will turn this one into a -1/3. That's not good. So instead, let's fix this 2. So let us now multiply the second equation by -2, add it to the first equation. Add -2 times the second row to the first row. Okay, so there we go. We now have no y in the first row, but there's no equation that has only z in it. Okay, so what are we going to do? Well, let's go back to our lecture file. So I have here a copy of the final matrix that we got, and we said if you have a system of linear equations, you can make the augmented matrix. Well, that works in both directions. So now that we have this new augmented matrix, let's write down the corresponding system of equations. Now remember, we didn't put the vertical lines, so we just have to remember that that makes equal signs in the actual system of equations. So we have x plus 0y minus 4z equals 2. 0x plus 1y minus 3z equals 1. 0x plus 0y plus 0z equals 0. Okay, so all of these numbers correspond to coefficients in the system of equations. We have a matrix here which is very special, and that's why we stopped at that point. It's an example of a matrix in what is called a reduced row echelon form, or REF. Now, how do you know that you have reached the REF? There are 4 characteristics. All the rows consisting entirely of zeros, if there are any, are at the bottom of the matrix. So here we have all zeros in the 3rd row. The first non-zero entry of any row is the number 1. So this entry is called a leading one. And of course, that's the reason why we made 1x here and 1y over here. Now, if the next row is non-zero, its leading one has to be to the right of the previous leading one. So the leading one on the 2nd row is to the right of the leading one in the 1st row. Furthermore, we say that the matrix is in REF if all the entries above a leading one are also zeros. So this leading one has 0 above it. There are only 2 leading ones. There's obviously nothing above that leading one, but above this leading one is a 0. So a matrix that has the first 3 conditions satisfied is said to be in row echelon form. But if you also fulfill the last condition, where all the entries above the leading one are also 0, then you get a matrix which is in REF. Okay, so let's finish off this problem. Now, we have all of these zeros, so of course we can simplify the first equation to just say x minus 4z equals 2, and the second one says y minus 3z equals 1. The third equation says 0 equals 0. Okay, so if that bothered you earlier, let's talk about it now. That is a true equation. 0 is equal to 0. So it's a true equation, but it doesn't really tell you anything about x, y, or z. In the next video, we will consider what will happen if you get 0 equals 1. Well, actually, why don't we talk about that now? Is 0 equal to 1? No, of course not. If this ever happens, then something went wrong. What does that mean? It means that your system has no solutions. But in this case, happily, we do have solutions to our system. And we're about to get that now. So what's going on here? We have our leading ones for x and y. Because of that, we will call x and y leading variables. So let's insert that over here. Our leading variables are x and y. And we noticed we didn't get an equation with z on it in it by itself. Okay? That's not a problem. What that simply means is that z is what is called a free variable. Z can be any real number. Our free variable is z. So z can be any real number. Okay, and then what do we do? Now that we know that z can be any real number, we can solve for x in terms of z. So we get x equals 2 plus 4z and y equals 1 plus 3z. Okay, and we can summarize our solution by creating what's called a solution vector. So we will put the values for x, y, and z in a vector form. Our x is 2 plus 4z. Our y is 1 plus 3z. And our z is just z. So there we go. Those are all the solutions to our system of equations. X is 2 plus 4z, y is 1 plus 3z, and z is just z, where z is any real number. Now, because z can be any real number, there are an infinite number of solutions to our original system. So we can ask, for example, what is the simplest solution to this system? Well, I would think that the simplest value for z that we can plug in would be z equal to 0. So let z be equal to 0. And if z is 0, what is the value of x? We will get 2 plus 0 or 2. And y will be 1 plus 0 or just 1. So this is an example of what is called a particular solution. So we can say, in particular, if z is 0, then we get the solution x is 2, y is 1, z is 0. So we can summarize that with our solution vector. X is 2, y is 1, and z is 0. Okay, well, let's ask another question. Is there a solution, for example, when x is 0 instead of z? So we can ask, can x be 0? Is there a solution where x equals 0? Okay, well, this is our expression for x. X is 2 plus 4z, and we can easily set that to 0. So we want 2 plus 4z equal to 0. And from this, of course, z has to be negative 1/2. So we get a fraction. And now that we have that, we also want y. So y will be 1 plus 3z, and that will be 1 plus 3 times negative 1/2. Negative 3/2 plus 1, I believe that becomes negative 1/2. So our solution vector will be xyz is 0 for x, negative 1/2 for y, and negative 1/2 also for z. Okay, so that's our solution vector. That's interesting. So y and z are the same values. So we can ask, So we can ask, is there a solution where x equals z? Okay, why not? So let's copy our solutions over here. So we want x to be equal to z. Okay, so we want 2 plus 4z to be equal to z. So we get, let's see, move the z to the left, 3z equals negative 2. So z is negative 2/3. All right, so that is our z. That should also be equal to x. Okay, so let's check. If z is minus 2/3, we'll get minus 8/3 plus 2. That'll be 6 minus 8, negative 2 over 3. But we also would want our y. So y will be 1 plus 3z. So that is 1 plus 3 times negative 2/3, and that is, so that is just negative 2 plus 1, negative 1. So our solution vector is going to be x and z are both negative 2/3, and y is negative 1. Okay, so that is our solution vector. Let's label it over here. All right, we have reached the end of this video. We will continue with systems of linear equations in our next video, where we ask the question, is a certain vector part of the span of a set of vectors? So thank you for watching this video. As usual, you will find me on Facebook. You will find the 4th edition on Facebook and on kendallhunt.com. Until next time, thank you for watching this video. Have a nice day.